Welcome to this NPTEL lectures on robotics, basics and advanced concepts. Till now, we have looked at robots which have fixed base. They are either serial or parallel. In these lectures, we will now look at wheeled mobile robots. Okay, so there are three lectures in this topic. The first topic is on wheeled mobile robots on flat terrain. The second topic is on wheeled mobile robots on uneven terrain. And then we will look at kinematics and dynamics of wheeled mobile robots on uneven terrain. Okay, there are many aspects of wheeled mobile robots, things like obstacle avoidance, sensing, intelligence, map making, and so on. But in these lectures, we will concentrate on the kinematics, dynamics, and basically modeling and simulation of the wheeled mobile robots. So let's continue wheeled mobile robots on flat terrain. So we'll first look at some wheeled mobile robots. I will introduce you the topic of wheeled mobile robots. Then we will look at different kinds of wheels and their modelings. Okay, a wheeled mobile robot by definition should have a wheel. So there are different kinds of wheels. Then I will very briefly tell you the kinematics of wheeled mobile robots on flat surfaces. One of the important aspects of wheeled mobile robots moving on flat surfaces, or for that matter on any surfaces, is this notion of slip. Okay, the wheels of a wheeled mobile robot, when it is moving on a surface, will always slip. Without slip, actually, we can't even move. So we will look at how to model this wheel slip. And we will next look at modeling of a wheeled mobile robot with omnidirectional wheels. So this is a new kind of wheel which has 2 degrees of freedom. Okay, and we will look at how to model a wheeled mobile robot with omni wheels. And we'll look at some simulations of wheeled mobile robot with omni wheels. So many robots have been designed to have mobility. Okay, so for example, they can move on surface, in water, and in air. In these lectures, we will look at robots with capability of mobility on a surface. Okay, so we will not worry about drones and robots which can move underwater and so on. So the earliest examples of wheeled mobile robots are automated guided vehicles, also called as AGVs, with wheels, and these were used on flat factory floors. Okay, so AGVs could take material components from one station to another station and in an automated manner, or sometimes they would be guided by some wire or some tracks which were put on the factory floor. More recently, autonomous robots with legs and or combination of wheels and legs, which are also called hybrid, have been built. Okay, so one of the robots which I had shown you in one of previous lectures was a quadruped. So that is a mobile robot with 4 legs. The vast majority of wheeled mobile robots, also sometimes in these lectures I will say WMR, are wheeled mobile robots. Okay, because they are very efficient, they can move much faster than legged or tracked vehicles. Okay, there is an advantage of legged and tracked vehicles because they can navigate rough terrain. So for example, tanks and bulldozers and some things, they have a track because they need to go over uneven terrain. Autonomous vehicles are used in industrial environments to move material, parts, and finished goods from one place to another. They are used in military and security applications, okay, like tanks, or even autonomous vehicles which can patrol a surrounding. They are also used in hazardous environments such as inside nuclear reactors or in deep sea bed. Nowadays, these autonomous vehicles also provide mobility to handicapped persons. Okay, so we have autonomous wheelchairs on which a person can sit, and then these wheelchairs can navigate on roads or through crowds and so on. Autonomous vehicles are nowadays very popular because they are on Mars. Okay, so there is this wheeled mobile robot which is exploring surface of the Mars in an autonomous fashion. The analysis of WMRs involve kinematics, dynamics, control, sensing, motion planning, obstacle avoidance, many things. Okay, so there is something called map making, there is something called SLAM, simultaneous localization, and other things. Okay, so we need to worry about many aspects when we look at wheel mobile robots. In this set of lectures, we will only look at kinematics and dynamics. Okay, we are not going to look at sensing, motion planning, obstacle avoidance, and so on. A little bit of control will also be discussed. So a few examples of WMRs. So on the top, we have this Mars rover from NASA. Then we can have some wheel mobile robots. This is from internet, which is moving over uneven terrain. We also have AGVs. These were the first wheel mobile robots, these two. And then we had built a wheel mobile robot with what are called as Omni wheels. Okay, we will discuss this in more detail. This robot was built in our lab. So what is the definition of a wheel mobile robot? According to this Muir and Newman in 1997, a wheeled mobile robot is a robot capable of locomotion on a surface solely through wheel assemblies mounted on it and in contact with the surface. Okay, a wheel assembly is a device which provides or allows relative motion between its mount and the surface on which it is intended to have single point of rolling contact. Okay, so the important word is it is capable of locomotion on a surface. The other important word is single point of rolling contact. Most of the time, this is not really correct. The contact is never point contact. Okay. In practical wheels, due to the deformation of the wheel, there is area contact. And there are different types of wheels used in wheel mobile robots. First is conventional, then there is omnidirectional wheels and ball wheels. So we'll see later. So this has 1 degree of freedom, this has 2 degrees of freedom, and this has more degrees of freedom. Okay. So what is a conventional wheel? It is basically something very similar to a caster wheel. So this is the wheel, there is an axle, okay, and then there could be a hub motor or there could be a motor mounted somewhere which will transmit the motion to this wheel. This is a normal standard wheel which is used in most wheel mobile robots. Okay, so there is a connection point to the body. So conventional wheels most commonly used. So they can rotate about this wheel axis, okay, and it can be also steered. So the steering is from the body. Then we have what are called as omnidirectional wheels. So basically this is the wheel, but on the wheel is made up of barrels which can roll in a perpendicular direction. So the whole wheel can rotate about this axis. So you can see there is a motor and we have mounted some encoder to measure the rotation. But these balls themselves can rotate, and the shape of the ball is such that when it is on the surface, okay, there is a point contact. Okay, so there are barrels in the periphery. The barrels can rotate at an angle to the wheel. In this figure, it is 90 degrees in the figure, but it can be at any other angle. The barrel rotation is typically not actuated. Okay, so the barrel rotation leads to sliding of the wheels. So at one place, if the barrels rotate, the wheels can slide not in the driving direction, but perpendicular to it. And there are 2 degrees of freedom in each wheel. So it can rotate and it can also slide. Okay. So ball wheel is another kind of robot. So it is basically nothing but a spherical ball, okay, which can rotate about 2 axes. Okay, these are called ball or spherical wheels. So in this is of course a toy ball wheel. Okay, so there is a drive mechanism which is very complicated, but it is not shown here. And then there is on the top a way to connect to the body of the robot. So that it requires a very complicated drive and rotation measuring arrangement. Okay, so most of the time, simple 1 degree of freedom wheels like this conventional wheel is used. Sometimes this omnidirectional wheels are also used. These omnidirectional wheels are also called Swedish wheels. okay, in literature. So let's look at a single wheel kinematics. So basically a single wheel can be modeled as a disk on a plane. Okay, so this is the plane, this is the XY plane in some reference coordinate system 0. The axis of rotation of the wheel is this way and the rotation angle is theta. Okay, so let's assume that there is a contact point on this wheel which is at some x comma y. Okay, and then this wheel is tracing this path on the plane. There is also a tangent at the point of contact which is shown here. Okay, so the configuration space of this wheel consists of the following parameters. One is this contact point, which is x and y, and it is also the steering of the wheel or the direction in which the wheel is instantaneously moving along this tangent. Okay, so that is an angle phi. So this x, y, phi, where phi is the steering angle, are enough to describe the motion of this wheel. If the wheel is very thin, okay, then one more thing is required. The wheel can also tilt about the vertical axis, about this axis. Okay, so then the tilt should also be considered. The rotation of the wheel theta does not appear in the kinematics. We will see later. Okay, because we want to look at what is happening instantaneously. So if the wheel is rolling without slip, the motion is only along the tangent to that curve. Okay, and we can write the expression x dot sine phi minus y dot sine phi equal to 0. Okay, remember the wheel is not slipping and it is moving along this tangent. Okay, the velocity perpendicular to this tangent vector is 0. Okay, this is what the basic equation of a single wheel or a disk which is rolling on a plane without slipping. Okay, this is a non-holonomic constraint. Okay, what do we mean by non-holonomic constraint? We cannot integrate this equation and obtain an expression like f x y phi. Okay, if it were integrable, then it is just a normal holonomic constraint. Okay, the constraint is in terms of q dot, which is in terms of x dot, y dot and phi dot, and not in terms of x, y and phi. Okay, so the constraint restricts the q dot variables by this equation. However, it does not restrict x, y and phi. Okay, so how do we know it is non-holonomic? Okay, we assume that this x dot sine phi minus y dot sine phi cos phi equal to 0 can be integrated. So if it were holonomic, this constraint could be integrated. So this means there is an existence of a function f of x, y, phi equal to 0. Okay, it is 2 degrees of freedom. So choosing any 2 out of x, y and phi automatically determines the third because of this function. Okay, it's a single function is x, y and phi. So if I choose any 2 of them, let's say x and y, phi will be automatically determined. Okay, so phi will be equal to phi star, which is fixed. As an example, if x equal to 0, y equal to 0, then at that point, if there were a function like this, phi will be phi star and fixed. No other value of phi is possible. Okay, so this is clearly not true. It is false. Okay, why? Because think of the disk at this point at 0, 0. Okay, I can easily rotate this disk about this direction which is normal to the plane at point of contact at 0, 0. So I can rotate the disk at the same x comma y and I can achieve any phi. Okay, so that is what is mentioned here. So this is clearly false because any phi is possible at 0, 0 by simply rotating the disk about the normal. Okay, so hence such a function does not exist and hence this equation cannot be integrated. So I gave you an example of x equals y equals 0 and phi is fixed. You can also do the same thing for if I choose x equals something and phi equals something, y will be fixed, but then that is also not true. I can achieve any y. So the kinematics of a single wheel is given by x dot, y dot, phi dot, cos phi, sin phi 0 into v into 0, 0, 1 omega. Okay, so v is the forward speed and w is the steering rate. So the wheel is rolling forward at some velocity v, and it is also being steered by some angular rate. Okay, so that is given by this. Let's look at a two-wheeled mobile robot. Okay, a two-wheeled mobile robot is nothing but a bicycle. Okay, so in a bicycle, we'll have four generalized coordinates. One is some x comma y, which is the point of contact of, let's say, the rear wheel at this place. Psi, which is the orientation of the body and rear wheel with respect to the x-axis. So this is the x-axis, this is y-axis, and this is the fixed reference coordinate system 0. So at x and y, there is an angle psi, which represents this body and the orientation of the rear wheel. And then there is a steering angle of the front wheel. Okay, so those of you who have ridden a bike, you know that the front wheel can be steered. Okay, and the back wheel can be represented by x, y, and some orientation with respect to a fixed coordinate system. So there are two rolling constraints in each wheel. So we have x dot sin psi minus y dot cos psi is equal to 0. And we also have x dot sin psi plus phi minus y dot cos psi plus phi minus L psi dot cos phi equal to 0, where L is this length between the two wheels. Okay, so the first one is very similar to one single wheel, and the second equation is for the front wheel. And we can write the kinematic equations of a two-wheeled bicycle as x dot, y dot, psi dot, phi dot is equal to some cos psi, cos phi, sin psi, cos phi, sin phi by L into some Vf. Vf is the forward velocity of the wheel into 0, 0, 1 into omega, which is the steering rate. Okay, so this is the expression which gives you the four generalized coordinates, how they change with time. The line perpendicular to the front and rear wheel velocity meet at a point. Okay, so this is called as the instantaneous center of rotation of this bicycle. Okay, so you can think of the motion of this bicycle as rotating instantaneously about a point in this xy plane. Okay, later on we'll see that this instantaneous plays a very important part when there is slipping. Okay, if you have a three-wheeled robot, okay, mobile robot, so this is like a tricycle. Okay, in this picture, the front wheel is steered. The two rear wheels are at a distance from each other, at some distance. Okay, and then the body of this tricycle makes an angle psi with the x-axis. We will assume that the center point between these two rear wheels is some x and y. Okay, the wheel speed for each wheel is theta dot ri, where I is radius of the wheel. So one rear wheel is driven, and the speed of the second rear wheel must adjust so that there is a single instantaneous center of rotation. So if this velocity is like this, and this velocity is different than when it is instantaneously meeting, okay, at this point, so then it is not possible to drive. Okay, so typically in a tricycle, one of the rear wheels is free, or in an automobile, with three-wheeled automobile, there is a differential. So as you take a turn, the speeds of these two rear wheels will adjust such that there is an instantaneous center. Okay, the kinematics of a tricycle is similar to a bicycle. We have the same set of variables. C determines the relationship between r, theta dot, ri, l, psi and phi. Okay, if no single C, wheel slip will occur. Okay, so you can think of that this wheel is rotating faster, so it has some velocity vector. This wheel has a velocity vector such that the instantaneous center, or these three wheels have velocity vectors such that C doesn't exist. there is not a single C, then one of the wheels must slip. Finally, let's look at a car-like mobile robot with 4 wheels. Okay, so if you have a 4-wheeled car-like mobile robot, the steering angle of the front wheel is different in a turn. So these 2 wheels need to be steered differently. Otherwise, again, the instantaneous center is not there. Okay, so there are sophisticated linkages which make sure that when you steer the car, okay, the 2 wheels rotate differently. Okay, so the inside wheel is phi I and the outside wheel is phi 0, and you need to make sure that this cotangent of phi I minus cotangent of phi 0 is d by L. So d is this and L is this. Okay. If you have multi-axis vehicles like a truck and a trailer, the steering of the front wheel to the left results in the right motion of the wheels of the third axle. Okay, so if you think about it, if you have a driver who is driving a truck with a trailer, if the front wheels are moved to the left, the rear wheel will move to the opposite direction. Okay, so these are called non-minimum phase systems. Okay, and they are very difficult to analyze, or more difficult to analyze and model. So we will not look at these 4-wheel and tractor trailer type of arrangements. Okay, so most of our discussion will be based on a 3-wheeled mobile robot in this set of lectures. Let's look at omni wheels. So basically we have these 2 rows of barrels, okay, on a single axis. So these are 6 equally spaced free barrels on the periphery. So 1, 2, 3, 4, 5 and 6, okay, 60 degrees apart. So each barrel can rotate about this barrel rotation axis, and the wheel itself can rotate about the wheel axis. Okay, so there are 2 rows of barrels which were used in our design, such that one barrel is always in contact with the ground. Okay, if the barrels are at an angle, this axis is not 90 degrees, so then we can get away with 1 row of barrel. Okay, so the distance between the point of contact from the wheel center changes. So this is what happens. So if the wheel is rotating such the point of contact is on this barrel, then after a while the point of contact is on this barrel. So the distance from the center of the platform to the point of contact will change. Okay, this happens in omnidirectional wheels. We can also quantify these 2 rotations about the barrel rotation axis and about this wheel's axis as theta dot, which is the rotation of the wheel, and then this sliding speed, which is psi. Okay, this is the rotation of the barrel. So the 2 components of the velocity of the wheel center for a general case of a barrel at an angle alpha to the wheel axis will be r theta dot plus sigma cos alpha and sigma sine alpha. If alpha were 90 degrees like this drawing, then the components of the velocity are r theta dot and psi. You can see r theta dot is in this direction like any other wheel, and sigma is perpendicular direction. Okay. So if you have an WMR with 3 omnidirectional wheels, okay, then we can show that it can trace any path on the plane. Okay, so let's look at this WMR with 3 omni wheels. So we have 3 wheels, so which have sigma 1 this direction, v1 which is r theta dot in this direction, similarly sigma 2 and v2, and sigma 3 and v3. Okay, so and these 3 wheels are 120 degrees apart. The direction of this first wheel is at an angle psi, and this point where the omni wheel is, the center, is at x comma y. So no steering wheel is required. Okay, the wheel rotation is theta I dot for each of these 3, and the kinematics with no slip at the wheels can be represented by theta1 dot, theta2 dot, theta3 dot is equal to 1 by r, where the radius of the omni wheel is r, 0, 1, L1, L2 and L3, and then you will have this minus root 3 by 2, minus half, and so on. This will be related to x dot, y dot, and psi dot. So x dot, y dot, and psi dot are the velocity, linear and angular velocity of this platform. Okay. So this L1, L2, L3 are nothing but the contact points from this center of the platform. So we can write theta dot as a vector is equal to R, some matrix R, into x dot, y dot, psi dot. Okay, so this matrix R is analogous to the manipulated inverse Jacobian. Okay, remember in the Jacobian of a normal manipulator, it was some V is equal to Jacobian times theta dot. Whereas here we have theta dot is equal to some matrix times V, roughly speaking. Okay, so V here correspond to linear velocity and angular velocity. So this matrix can be inverted. So you can see it looks like it can be inverted. Okay, so and it is true, it can be inverted. So hence, if you want an x dot, y dot, psi dot, we can find out the theta dot and we can go backwards. Okay, so we can obtain the theta dot for a desired x dot, y dot, psi dot. Okay, and we can also obtain x dot, y dot, psi dot as some r inverse theta dot. Okay, so what this equation is telling you, since the matrix R is invertible, the WMR is controllable with theta I dot. Okay, so you can think of it that I can move this vehicle at some desired velocity by suitably finding out what is theta dot. We can also obtain the sliding speed, which is sigma 1, sigma 2, sigma 3 vector in terms of x dot, y dot, psi dot. However, that matrix relation, so sigma dot is equal to some another matrix into x dot, y dot, psi dot, but that matrix is not invertible. Okay, so hence what it is telling you is that this wheeled mobile robot with omnidirection and wheels cannot be controlled by sigma I alone. Okay, so you can think of it this way, that I need to rotate the motors of 3 wheels to give any linear and angular velocity. But if I can somehow slide the wheels in the perpendicular direction, then this analysis is telling you that we cannot move the robot from one place to another place. Okay, or we cannot achieve any desired linear and angular velocities. So, okay, so let's continue. We need to now look at slip. Okay, so we need to model the slip firstly. So for rolling without slip in a conventional wheel of radius r, the wheel center velocity and the wheel angular velocity omega are related by v equals r omega. Okay, this is obvious, straightforward. Okay, now either the wheel and or the ground must deform for generating tractive forces to drive the wheel. Okay, so if you have a pure point contact and both are rigid, then we cannot generate a force which will drive the wheel. Okay, think about it. So it is to achieve any tractive force, there must be some deformation. Okay, so unless you have a deformable wheel or a deformable wheel and a ground, okay, which is deformable, wheel slip cannot occur. And without a deformable wheel and or ground combination, we cannot move. So wheel slip needs to happen to generate tractive force, and for that we need some deformation either in the wheel or in the ground. The wheel slip can be defined as the as the ratio of theta dot minus omega star divided by y. Okay, so let me explain. So theta dot is the wheel angular velocity. Omega star is v by r. Okay, so if theta dot is equal to v by r, lambda is 0. Okay, however, v by r, which is omega star, and theta dot, they are not equal. So the wheel is rotating much more than if it is slipping. So this quantity is some number, and we divide by y, which is also omega star. So what it means is, this is some number. It is a non-dimensional number. Okay. So when omega star is greater than theta dot and y is equal to theta dot, okay, so y is equal to omega star when omega star is greater than theta dot. Is that true? Yes. Okay, and y is equal to theta dot when omega star is less than theta dot star. So the above implies that this lambda lies between -1 and +1. As I said, it's a number. So we have pure rolling when lambda is equal to 0, which means theta dot is equal to omega star. We have rolling in place at the same place and not moving forward when lambda is equal to 1. And we have skidding when it is not rotating but still moving forward when lambda is equal to -1. So in this definition, we captured all these three possible ways a wheel can move on a ground. So it can do pure rolling, it can do rolling at one place without moving forward, and it can do skidding. Skidding is basically not rolling but moving forward. So let's look at the translational and rotational dynamics of a single wheel, okay, which is deformable wheel, so that there is some traction. Okay, so there is a tractive force. So there is a tractive force F of t which is applied. Okay, so think of a wheel like this. So if there is no tractive force, it cannot move forward. Okay, so if you are on a bicycle and if there is no tractive force of the wheels, the bicycle cannot move forward because there is no external force which is driving the bicycle forward. If you rotate the pedal, that is not an external force in the direction of motion. So there must be a tractive force in the direction of motion, just by Newton's law. So it turns out that this tractive force F of t will be equal to m of the wheel, which is mass of the wheel, into x double dot. So this is the direction x dot of the center of the wheel. And since we are applying a torque via motor, this torque will be equal to j omega, which is the moment of inertia of this wheel, into theta double dot, plus the torque due to this tractive force, which is Ft times r. Okay, where x double dot and theta double dot are the linear and angular acceleration of the wheel. So in state space form, this can be written as x dot equals to fx plus g tau. Okay, what else is happening? There is a ground reaction. So as you can see, this tractive force must be related to the ground reaction. Okay, so it will be some coefficient of friction or addition coefficient into n. Okay, or a function of n and this coefficient of friction. Okay, so it turns out that this, in this state space form, it is not locally controllable if the tractive force is constant. Okay, so if you have a constant tractive force or a 0 or some number, it cannot be controlled. So this tractive force Ft must be a function of x dot and theta dot. Okay. So typically what is Ft? As I said, Ft is a function of the normal reaction n and some kind of addition coefficient or coefficient of friction mu a. The mu a itself will change due to wheel slip. Okay, so the coefficient of addition or friction will increase if the wheel slip is increasing up to some peak. Okay, in the other direction it will increase up to some peak value. After that it starts decreasing. Okay, this is a typical plot of a wheel which is slipping and rolling. Okay, so this was known This has been known from automobiles and aircraft wheels which are landing and so on. Okay, so typically mu a is a function of wheel slip and has a maximum value, mu a peak. The tractive force developed is always a function of this mu a, which is a function of wheel slip and the normal force. Okay, so it is not just simply mu into n. Mu is not a constant. If you were doing basic mechanics problem, the friction force is mu times n, where mu is a constant. But in case of wheels rolling on ground, okay, mu is a function of the wheel slip. So actually 0 magnitude of this tractive force is less than or equal to mu a into n. Okay, so the proper sign of tractive force must be used for acceleration of braking. So let's go back to this plot once more. So we know that this addition coefficient or friction coefficient changes with wheel slip. So what you can see is for some region, which is from here to here, as the wheel slip increases, the addition coefficient increases. So this region is called the stable region, whereas after some lambda, when the addition coefficient starts decreasing, okay, that is an unstable region. So as you can see, if it is slipping, but the tractive force is decreasing, then it will slip more. So it is unstable. Okay, so it is very important for any wheeled mobile robot to be operating in this region. Okay, and what would be the best place to operate? We would like to operate very close to the peak, but on the left hand side, because remember, if the mu a is large, the tractive force is large, and hence we can move faster. Okay, so typical region is on the left of this peak, but as close as possible. We don't want to go on the right, because then it starts slipping more. It is unstable. We can also derive the equation of motion of this wheeled mobile robot using the Lagrangian formulation. We assume that the mass of the platform is mp, the inertia is ip. We can obtain the kinetic energy of the platform. We can also obtain the kinetic energy of each of the wheels. The inertia is ii. There is no potential energy at this stage because it is moving on a flat plane. We can also include the tractive forces at the wheel, Ft, torque at each wheel, tau I, and an approximate mu a versus lambda curve. Okay, we need to know how this friction force or friction coefficient or addition coefficient changes with wheel slip. So once we have assumed all these things, we can derive 6 ODEs, okay, which take into account the wheel slip. So we have mass times x double dot, y double dot, and then ip times psi double dot, then some Coriolis centripetal term. Then we have that R matrix which relates theta dot to the velocities of the platform, and we'll see later that this, or you can imagine that this R transpose into this Ft will give some kind of a torque. So just like tau was J transpose F, so similarly here R transpose F will show up, and R is the radius of each wheel which we assume. So this is the translational velocities and accelerations of the wheel. Okay, this is a translational motion of the platform. In addition, we have a angular motion of the platform, which is something like I into theta double dot plus the torque due to the tractive forces must be equal to the wheel torque. Okay, so nothing else is happening. So we have captured the effect of the tractive force by means of this mu a into lambda curve. And then we also have captured the kinematics using this R matrix. And then we have derived the equation of motion. The equation of motion will be 6 of them, okay, and look like this. So let's assume that we have a desired path, which is xd of t, yd of t, and psi d of t. So psi is the orientation of the one of the axis with respect to the reference x-axis. We can try a PID control, which is kv times x dot or e dot plus kp times e plus ki times e of integral e dt. Okay, this is a standard PID law where x is this quantity here. Okay, x is xt, yt is psi t. We can compute the Cartesian forces related to the wheel actuated torque by tau is equal to RT inverse Cartesian forces. Okay, so very similar to what we did when we have Cartesian motion of a serial robot. So we had some Jacobian matrix and it was related to the Jacobian matrix inverse and so on. So in this case, if you think a little bit about it, R is the inverse of the Jacobian matrix. So you have some transpose and then again an inverse to relate the motor torques to the Cartesian forces. We can also have a model-based control using ideal rolling, which is tau is alpha tau prime plus beta, where alpha is this R transpose inverse M star. M star was that mass matrix. Beta is R inverse transpose psi dot Q x dot, and tau prime is this PD controller scheme. So M star is M plus R transpose IR. So this is basically converting the mass matrix to for corresponding to ideal rolling. Okay, so this is a control scheme which is basically some part of it is PID or PD. This is PID, but we use PD here, and then this is the model based term. So this control scheme was used by one of the students long time back. We assume L1, L2, L3 is 0.5, R is 0.1 meters. Inertia parameters was taken as 50 kg and some IP was 5 kg meter square. The wheels were 2 kg meter square, and we set controller gains to KPI to 15, KBI to 2 square root of KP, means critical damping, and integral gain as 0.1. Okay, so then we can see what is the mobile robot doing with this choice of controller gains and this choice of control. So if I want the XD to go up in a ramp like this and stay at the same place, so what is the controller, this particular controller doing? You can see that the motion of the platform X looks like this, the dark line, whereas this dotted line is the desired X. Likewise, the desired Y was a constant value. I want to stay at the same place, so I want to go in some X direction. The Y also changes. It does not maintain YD equal to 0. Okay. So we can also see how the mobile robot traces a circular trajectory. Okay, so and we can try different addition coefficients. So remember, mu A is a value which you need to choose. It depends on the friction and various other parameters between the wheel and the ground. So the reference trajectory is a circle, and for different mu peak, so remember mu A has a peak value. So if you assume that to be 0.8, okay, or 0.2 or 0.08, so 3 different values, one very small, one medium, and one very large, you can see what is happening to the trajectory. So 3 is with 0.2, 4 is with 0.08, and the other one is with 0.8. So for a very large coefficient of addition or friction, okay, it comes very close to the reference trajectory, which is a circle. Whereas as the friction coefficient reduces, we can see it deviates from the trajectory. Okay, so this is one of the findings long time back, when we showed that if you do not model slip, okay, then we will not be able to track a desired trajectory in a wheel mobile robot. So modeling of slip and taking into account the slip which is happening at the wheels is very important in a wheel mobile robot. So as I said, the performance of the PID controller is quite poor. Maximum error in X is about half a meter. Maximum Y error is 0.2 meters. Model-based controller using ideal rolling as model performs slightly better. However, as the mu-a peak decreases from 0.8 to 0.08, so 10 times smaller, the performance of the model-based controller also becomes poorer. Okay, so the maximum radial error from the desired circular trajectory of radius 2 is approximately 1.7 meters. It's quite a lot. So hence it is important to model or take into account slip in wheel mobile robots, and this was later borne out by experiments also. Okay, so let's conclude this lecture. So in summary, WMR is very different from serial and parallel manipulator. Okay, why? Because the base is not fixed, it is moving. The wheel ground contact results in non-holonomic constraints. Okay, it is not a holonomic constraint as what happens in, let's say, a rotary joint or an SS pair. There the constraints did not involve the rates of the generalized coordinates. So the non-holonomic constraint does not restrict the configuration space, it does not restrict the generalized coordinate, but it restricts the space of velocities. Okay, so there is a relationship with the derivatives of the generalized coordinates. There are various kinds of wheels in use. We can have conventional wheels, omni wheels, and ball wheels. Conventional wheels rotate about the wheel axis and can be steered about the normal. Omni wheels can rotate about this axis and slide along another direction and also be steered. Okay, we can also steer the omni wheel. I didn't show you that, but it can be steered. Ball wheels can rotate about two different axes. Okay, so the WMR with 3 wheels is the simplest configuration. 4-wheel and multi-axle WMRs are more difficult to model and analyze. And finally, the slip, which is due to the deformation always present in the wheels, need to be taken into account in WMR dynamics and control. Okay. So in the next lecture, we'll look at wheel mobile robots on uneven terrain.